A2 Maths, Range and Domain. Well, what I'd like you to do is just have a go, starting off, something easy, have a go at sketching the graph of y equals 2x plus 3. So just pause there and have a go at that. Okay, so hopefully you managed to draw that linear graph, however you wanted to do it. It's not really a problem. The graph should look something like that, crossing at 3 with a gradient of 2. Right, just in your notebooks, just a couple of new definitions for you to write down. What we call the domain is the values of x that can go into the equation. So in the case of y equals 2x plus 3, the x value that you've got just here can work for any possible value. It doesn't matter what x value you think of, whether it's 2, whether it's 5, whether it's 9, you can definitely put it in there, and this equation always works. So in this case, what we would say is that the domain is all values of x, where x belongs to the real numbers. So this bit of notation just here, you've probably seen before. You might have seen it in certain exam type questions or questions in the textbook, or your teacher might have mentioned it last year. But just to make sure you're happy with it, what it means is x belongs to, so that weird little e symbol just there, that part is shorthand notation for belongs to, and r are what we call the real numbers. And for your sort of level of maths, what real numbers are is every single number you can think of. It could be the simple numbers like 1, 2, 3, 4, 5, which are the natural numbers, or it could be the negative numbers in there as well. But it can also be fractions, what we call quotients, or it could be things like pi and root 2. Every single number you can think of, you can put into this equation and it works. So the domain, this bit here, is every single possible number. Right, just as importantly, whatever number you put in, you can also get an answer out. So in this case, for this graph, you have what's called the range. Now the range of answers are the answers that you get out when you put one of the numbers in the domain into it. So for example, if I put the number 5 into it, 5 would be part of the domain. 2 times 5 plus 3 is going to get you 13. 13 is in the range. Put 5 in, bang, out comes 13. Okay, so the range are the y values and domain is the x values. The domain is like the home, that's where you start from, and you get a range of answers out when you put something into it. Now, exactly the same as the domain, every single value has a possibility of coming out. So for example, if I put the number 1 in, I'm definitely going to get the number 5 out. And it doesn't matter what numbers you can think of along this line, you can definitely get an answer that goes to it. Doesn't matter where it is, it's always going to have an answer somewhere. So in this case, the range is all the possible values, every single value you can think of, where y belongs to all the real numbers. Okay, so a bit of an easy graph to start with, an easy function. It has a domain of every single number and a range of every single number that comes out. Right, just repeat that, but this time I'd like you to sketch the graph of y equals x squared minus 3, and just have a think after you've sketched it, what's its domain and what's its range? Okay, so I'll pause, give you a chance to think about that. Okay, so hopefully you thought, I know what this graph is. It's the x squared graph, so that's just a quadratic, it looks like that, like the U-shaped graph, and I'm taking away 3 from it. So the whole graph, my U-shaped graph, drops down 3. So I should get something like that sort of shape. Now the other thing I've asked you to do is write down its domain and range. So we need to remember that domain is values that could possibly put into this function. So for example, in here, what numbers can you put in so that when you can still square them and take away 3? Now, if you think about it, what numbers can you put in? Well, you can put in normal numbers, 1, 2, 3, squared, fine. You can put in negative numbers. -3 squared is fine. You can put in fractions. A half squared is a quarter. It's fine. You can also put in something like √2. √2 squared is 2. So that works. In fact, whichever number you think of will definitely work in this function. So the domain is the same as before. All the values work in this function, so the domain is all the possible values of x, where x belongs to all the real numbers. So what about the range? What answers can you actually get out? Right, now this is where it's slightly different, because you can think about putting certain numbers in and you're going to get some numbers out. So for example, if I put the number 7 into it, I put 7 into it, I square it gets me 49, take away 3 gets me 46. 46 definitely works. But there is a problem. You put 0 into it, you're going to get -3 just here. And it doesn't matter which number you try and put in there, you're never going to get an answer that gets down to -4. You could try any number you like, any number within the domain, but you're never going to get -4 coming out. So -4, just there, is not within the range of answers that are possible. Every answer is possible, all of these, above -3, excuse me, but every number below -3 is not possible. So the range is all the possible values where y is greater than or equal to -3, where y is a real number. So every single number you can try always gets an answer out which is greater than or equal to -3. Okay, you can still get things like √14 coming out and things like that. You can still get pi coming out of it, but you will never get something like -6 or -5. Okay, just try the same exercise again. So I'll pause, give you a chance to plot down. It doesn't matter, it's in function notation. I just want to mix it up so you've seen both. Have a go at plotting f of x equals 1 over x and think about the range and domain again. So I'll pause. And let's see how you got on with that. So the graph of 1 over x, as you know, graph of 1 over x is that sort of shape. At least you should know it. Right, let's have a think about its domain. So what numbers can I put in? Well, you can put in nearly every number, can't you? You can put in 1, you can put in 2, you can put in 3, you can put in -7, you can put in a half. 1 divided by half is 2, you can definitely do it. You can put pi, 1 over pi works. But you can't put in 0. 0 does not work. That is why you have an asymptote just there on the actual graph, because you can't do 1 divided by 0. So what you'd say about the domain is you're allowed to put in every single possible value works in here, but not 0. So the domain is all the values of x where x does not belong to 0. Now I've decided to start leaving off the x belongs to real, just to save writing it every time, but you could write that as well, where x belongs to real numbers. What about the range? Well, think about all these values. I could put this value in, I get this one out. I could put this value in, I get this one out. I put that value in, I get this one out. In fact, I seem to be able to get any value I like. But it doesn't matter what value I put in, I'm never going to get this value, which is, as you can see, y equaling 0. It doesn't matter what I put in, I'm never going to get a value coming out as 0. So the range of possible answers I get out will be all the positive numbers, all the negative numbers, but not 0. So we can say that the range is all the possible values of f of x, but f of x cannot equal 0. It's the only one you can't get. Of course, you could write this the same as I just said, where f of x is greater than 0 and f of x is less than 0. That would be fine. So all the values greater than 0 and all the values less than 0. So another way of writing it. Both are acceptable. Okay, so same again, but this time something you might not have seen before, what's called a restricted domain. I would like you to have a go at plotting y equals 3x minus 1, so the graph of y equals 3x minus 1, but I'm only interested in the domain -2 to 4. So I only want the graph drawn between -2 and 4. Below -2, ignore it. Above 4, ignore it. for your x values. Right, just have a go at plotting that, see if you can understand what I mean. Okay, so I'll pause. Okay, so your graph is another linear graph like we started with, a gradient of 3, crosses at -1, but what's important is it is restricted. It starts at -2 and it goes up to 4. We ignore anything that goes further up and we ignore anything that goes further down. So that is a graph with a restricted domain, because I'm only interested in these values just here. So the question is now, is what would the range of that equation be? Okay, so again a pause, give you a chance to think about it, and let's see what you got. So if I want to put these values in, I can definitely get these values out, all of these, put that number in, I get that, put this number in, I get that, but it doesn't matter how hard I try, I'm never going to get a value down here, because there is no part that takes you to here. Okay, I'm ignoring it. So because I've got a restricted domain, I've also got a restricted range. And the range of answers I get out, very easy to work out. I put -2 in to the equation. -2 times 3 is going to be -6. -7, -1 is going to be -7. I put 4 into it. 3 times 4 is 12. 12 take away 1, 11. So the answer I'm going to get out is going to be all the answers between there. So the range is all the possible values of y, where y belongs to the real numbers, between -7 and 11. Okay, so just try that again, thinking about the endpoints as the important parts. Sketch the graph of y equals x squared, nice and straightforward, but restricting the domain between -1 and 3. Okay, so I'll pause. And let's see how you got on. So, if you've drawn the graph, there's the restricted domain. So it looks like that. We're ignoring the fact it carries on up there, and we're ignoring the fact it carries on up here. We're only interested in these two values. Now, if you did like I said a minute ago, just looking at the endpoints, this one causes a bit of a problem. Because if I put -1 into it, the answer I'm going to get out is 1 just there. And if I put the number 3 into it, the answer I'm going to get out is 9 just there. My range is not just the values between 1 and 9. And in fact, because this is x squared, I can go all the way down to 0. So always be very careful. It's not as easy as just looking at the domain and trying to put in the two endpoints. You've always got to look at the graph, think about what's covered. So although -1 gets us 1 and 3 gets us 9, the actual range of this function is anything from 0 up to 9. Can't go below 0 because it's a function of x squared. So all the possible values for the range will be anything between 9 and 0. Make it all possible to get. That's what I'm going to do. Just going to pause on that sheet. So take a bit of time with it. There are lots of different functions there. If you can manage to calculate what the functions are or work out what the functions are, that'd be great. But if you can't, that doesn't matter so much as working out the range and domain of each of those graphs. Some of the graphs you might not have seen before, but all of them you should be able to have a go at working out their range and domain. Okay, so pause it. Come back in about 10 minutes to do that exercise, I would say. That minute on each, and then we'll have a look at the answers. Okay, so let's see how you got on. So this first one, this is an asymptote here. So definitely not going to get those values out. Let's think about the domain first though. Looks like we can put in any values along this function just here. It's not a straightforward function, this one. By the way, I'm not expecting you to spot what function it is. It's not a straightforward one. It looks very similar to root x, but it's not, because root x just keeps on going. So we don't really mind what the function is. What we can do is say that it definitely works for any value greater than 0, because I can put all these numbers into it, that all these work. But the answers I'm going to get out are only going to be between 0 and 1. But most importantly, it doesn't equal 1 because the asymptote is there. So what you should have got is a domain for all x's, where x is greater than or equal to 0. And the range is all values between 1 and 0. Most importantly, don't include the equal to 1. It can't equal 1, as we can see there. Okay, right, have a look at this graph. It's a bit of a poor attempt at an x squared graph. As we know, the x squared graph, we can put any numbers we like into it. They would all come out. Doesn't matter what values are put into it. So the domain is definitely all values, and the range is any value greater than 0. Look, I can get these values out, these values. I can also get those values, but I can't get anything down here. So my domain is all x, my y is all y greater than 0. This graph is what's called the mod graph. You'll see these later on. What can I get put in the mod graph? It looks like I can put any values in. I can see that. If I drew a line up, I'd hit it. If I drew a line down, I'd hit it. But it doesn't matter what line I choose to go up, I'm never going to get a line that comes down here. So in fact, those two graphs are identical for their domain and range. A linear graph, all linear graphs that are not restricted by a domain have exactly the same domain and range. They work for every function, and you can get every function out. You can work for all values and you get all values out. This graph, hopefully recognise as a cubic graph. And as we know about cubic graphs, any number we put in definitely works. Doesn't matter what value we put in. And also what's important about the cubic graph is that it doesn't matter which value you put in, you should always be able to get any value out as well. Okay, the x squared is restricted, but a cubic function to the power 3 isn't. This graph here looks like the same as 1 over x, but because it's in the opposite sides, it's minus 1 over x, and it's exactly the same answer as before. Works for all values except for 0 and except for 0. This graph, hopefully you looked at this and thought, well, it's a bit like sine and cos. I would agree, it is like sine and cos. It's close to cos because it's got that reflection in this line, but because it's upside down, it would be a negative cos graph. Now for the cos and sine graph, not the tan graph, you can put any values into it. Any values work. Assign whatever numbers you like. But as you know, you are restricted to between two values out. So the range of the function is definitely going to be between 1 and minus 1, because that's the amplitude of the sine and cos graph. But you can put in any values. So the domain is everything, and the range is restricted to those two values. Okay, but it can equal them, of course. This graph, hopefully you recognise this as what we call the exponential curve. So the exponential curve does have an asymptote just here at y equals 0, but you can put any value into it. You can put any value you like into y equals e to the x, but you can only get set out values out. So in this case, all values can be put into it, but the only answer you can get out are greater than, but not equal to, 0. Okay, y equals e to the x, you can put in any value you like, but the only values you're going to get out are positive ones. And finally, this very interesting looking graph. So I wouldn't expect you to recognise this one. It's a graph which is similar to something like 1 over x plus 1 and x minus 1, some sort of graph like that. But what's important is to notice these are all asymptotes going on. So the range, if you think about it, we'll put these values in because they can hit a line, but not there, because it doesn't matter how far up and down you go, you're never going to hit the graph. Okay, so we can work for all these values up to minus 1, but not minus 1. Then once you get past there, you can definitely hit your graph. Look, if I go down, I keep hitting this bit here. But then when I get to 1, doesn't happen. Can't hit the graph. Doesn't matter how far up or down I go, so it doesn't work for 1. Past number 1, yes. Hit it, hit it, hit it, hit it, and keep hitting it here. So it's a graph that works for all values except for minus 1 and 1. So what values can get out? Well, this is where we work across. Yes, 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 these all work. But minus 1 doesn't. Doesn't matter how far across I go, I'm never going to hit the line. Once I get past that, yes, 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 these are all going to hit. Okay, so it's definitely going to be all values put in except for minus 1 and 1, and all values out except for minus 1. So you'd write it something like that. Okay, so hopefully you've got a better understanding, or at least a good understanding now, of the range and domain of functions. And the examiner will expect you to know how to write down domain and range for each of your functions. Okay, so just grab your notebooks again. Let's look at something slightly different. So this is the graph of the function y equals 2x minus 1, or f of x equals 2x minus 1. This graph is what's called a one-to-one function. So a very basic linear graph there is what's called a one-to-one function. Now, the reason why it's a one-to-one function is because every single value you put in, doesn't matter what it is, you pick something from the domain and you put it into this function, you get one unique answer out. So in this case, if I put in minus 2, I'm going to get 2 times minus 2 is minus 4, minus 1, minus 5. No other value will get me minus 5. The only value that get me minus 5 is minus 2. And just as importantly, no other value can get me minus 2 except putting minus 5 as my y value. So one value goes in, one value goes out. So this means it's a one-to-one function. That's important to make sure you understand what a one-to-one function is. There's another example. If I put the number 4 into there, then I'm going to get 4 times 2 is 8, minus 1 is 7. Nothing else can get me 7. And if I put 7 as my y value, nothing else will get me 4. Right, look at the graph of f of x equals x squared. Now this graph is not a one-to-one function. And the reason why it's not a one-to-one function is because when you put a value into it, say for example number 2, the answer I'm going to get out is 4. So I put the number 2 into it and I get an answer of 4. But that's not the only value that get me 4, because minus 2 can also get me 4. So it is not a one-to-one function. And what we can call that is what's called a many-to-one function. Many different values can get to one possible answer. Minus 2 gets me 4, 2 gets me 4. Many different answers get me one possible answer out. Now you don't have to learn many to one as a name. You just need to learn that this is not one-to-one. And what I'd advise you to do is recognize whether a graph is one-to-one or not one-to-one, rather than worrying about many-to-one functions. There's the example I just mentioned. One answer in there, but that answer can get 2 as well. Many different answers, numbers in, get me one possible answer out. And like I say, very technical there, but it's right. More than one value on the domain maps to a value on the range. Right. You can change a many-to-one function if you restrict its domain. And this is important for what we're going to look at later on. So if a one-to-one function, if you've got something like a many-to-one function, like I've got here, and I want to work with a one-to-one function, I can't just say I can't do it. What I can do is I can restrict its domain. And in fact, if I just ignored this part up to there and pretended that didn't exist, I would only have this part and that would work fine. In fact, that's what I could do. If I'm only interested in where x is greater than 0, I lose this part just here, and now I have a one-to-one function. One number in, one number out, one number in, one number out, because I don't have to worry about this side. Right. And the reason why that's important is when we look at inverse functions. So you've done some inverse functions at school, you would have done some rearranging, changing the subject, those types of things, but you wouldn't have really done it to do with range, domain, and inverse, and one-to-one functions. So an inverse function maps a point on the range back to a point on the domain. So if you inverse something, it takes you back. And why this is important is it has to be a one-to-one function. Because if it's not a one-to-one function, when you're trying to map back, you don't know where to go to. So for example, if I said to you, I square a number, I get the answer as 4, you could say, well, your number is 2, or you could say your number is -2. You don't know which one it is. So because it's not one-to-one, it can't have an inverse. So just get those two notes down in your notebook. And let's have a look at an example of a function. So if I want to find the inverse of the function 3x minus 4, I know it's a one-to-one function. It's a one-to-one function because it's linear. Any value I put in for x gets me one unique answer out. So I'm allowed to find its inverse. And the way you find an inverse, once you recognise a one-to-one function, is exactly the same as your GCSE skills of changing the subjects of the formula. So the first step, when we're trying to change it, is write the function as an equation. Let's make it easy for ourselves. Rather than that function notation, f of x, let's make it easy for ourselves and just change it to y equals. So if I change it to y equals, it's a little bit easier to rearrange now. I want to change it so x is the subject. Now, because it's an inverse, one thing you should do straight away is, because you want to rearrange it, then you want to make x subject. So the first thing you can do is take that x value. What's going to happen? We're timesing it by 3. We're taking away 4. So let's get rid of this take away 4. Let's add it to the other side. And then I can divide by 3. So that algebraic step there of rearranging, basic GCSE algebra skills, you all know how to do that, I hope. Now then, once you've done that bit, what I need to do is, because I want the inverse, I don't want x and y that way round. I want to swap them round. I want to replace x for y and y for x. Now I can do that, and I can change those around, so I can write it as y equals x plus 4 over 3. And then also, because I changed from function notation to start with, I want to go back into function notation at the end. So I'm going to write it like this. Notice my x's and y's have changed, and my y value has become function notation because I decided at the start function. Now you don't need to change y into it at all if you don't want to. It's just a bit easier to rearrange. Notice there's a couple of things that you should spot with function notation. -1 is always talking about the inverse. You will have seen that before with things like sine to the -1 x, which was the inverse function of sine on your calculator. Okay, or tan or cos to the -1. So also some of your calculators will have -1 as a 1 over x function. Okay, right. So I'd like to plot the graph and its inverse function on the same set of axes. So I'm going to pause there. I'm going to give you a chance to have a go at working out the graph, draw the graph yourself. I want you to also have a go at rearranging it so that you've got its function, inverse function. Okay, as you just saw, you try it again, and then plot that on the same set of axes and just see if you can spot what I'm getting at there. So I'm going to pause. Right, let's see how far you got and see if you spotted what I was looking for. So there's my two graphs. There's the original graph. There's the function f of x equals 3x minus 4. The other graph that you should have spotted should have been f to the minus 1 f to the minus 1 of x is going to be x minus 3, x plus 4 over 3. And that's there. There you go. F to the minus 1 equals x plus 4 over 3. So I've plotted both of those on. Right, what I'd like you to do now is draw the line of symmetry on those two graphs. So depending on how accurate it is, just have a go at drawing your line of symmetry and see if you can work out the equation of that line of symmetry. So again, I'll pause and let's see how you got on. So hopefully you'd notice it's actually the line that cuts straight through the origin and goes up at exactly 45 degrees. The values you've got there where it crosses should be ones that are exactly the same in both of those. So the line of symmetry, which I just asked for, is going to be the line y equals x. Now in a lot of ways that should make sense, because when you're finding an inverse, what you are doing is swapping the y's and the x values around. Graph y equals 3x minus 4, the inverse to it would be x equals 3y minus 4. They're the inverse of each other because you just swapped your x's and y's over. So it's quite logical that the line of symmetry should be y equals x. And in fact, that would be my bit of advice. If you were ever trying to find the inverse, the first thing you should do, after writing it with y, is swap them out straight away. So if I've got y equals 3x minus 4, the first thing I would do is write it as x equals 3y minus 4, and that is the inverse. I would then rearrange it. So the graph of the function and the graph of its inverse is always a reflection in the line y equals x. Just grab that fact down in your notebooks. It's an important fact. The graph of the function, the graph of its inverse, is always a reflection in the line y equals x. And that also leads to another important fact. This is one that's easily overlooked. The domain of a function is the same as the range of the inverse function. So the domain of the original function is exactly the same as the range of the inverse function. And also, same sort of way round, the range of the function is the same as the domain of the inverse. So they basically swap places. So the domain and range are swapped between the function and its inverse, and so are these two. Now the reason why this is an important fact is because you could get an exam question where they give you the domain of the function, and later on they will ask you the range of the inverse. And they'll do it in a clever way, so it's not really obvious, but you've got to spot it. So if the domain of the function is something like x is greater than 4, is where it works for, later on when you talk about the range of the inverse, you would say, well, y can only be greater than 4. Those two functions are just swapped over. What I'd like to do now, have a go at completing exercise 5.1 on page 247. Gives you a bit more practice at range, domain and inverses.